Welcome back. So we looked at the stability criteria for a thermodynamic system, and we essentially said that a system goes into an equilibrium by maximizing entropy or alternatively minimizing internal energy. Now this we had seen in an earlier lecture that this would mean that d2s must be less than equal to 0, and this means that d2u is greater than equal to 0. But the idea now is, what does it really mean for the system? This is all very good. I mean, I have written down an expression, a differential form of my stability criteria, but what in real life, how does this stability criteria translate to the system? So for that, we want to consider u as a function of S and V. So essentially, I am going to focus on the minimization of the internal energy. One can also do the maximization of the entropy, and one should expect to get this, one should get the same result. Now clearly here, if I write down the change in the internal energy, this would be del U del S volume constant time ds plus del U del V entropy constant time dV. I now want to calculate the second, d2u, and for that I can just write down this way, treat du as a function, and once one does this algebra, this calculus, one will come up with the expression ds square plus del 2u del v2s dv square plus del 2u del s del v. There's going to be a 2 factor du this is dv ds. The 2 factor comes in because essentially we have said that the mixed derivatives are equal, which means that del 2u del s del v is equal to del 2u del v del s, and that essentially follows because u is a state function. Now I can write down this in terms of the derivative. So if you recall, then I know that del U del S volume constant is temperature, and del U del V entropy constant is minus pressure. So if I use this, then it follows that d2u is equal to del T del S volume constant ds square plus, so it's minus because this is del P del V entropy constant dV square plus twice del T del V entropy constant dV ds, and our minimization principle means that this must be greater than equal to 0. So question is what restrictions? So this must be true for any arbitrary variation in S V. But what does it really mean? Now for that, let's for a second step back and look at the following inequality: ax square plus twice bxy plus cy square is greater than 0 for all real values of x and y. Now clearly the obvious thing that you should say, or that will come to the mind, that if this inequality is true for any real value of x and y, this would mean that a must be greater than equal to 0 and c must be greater than equal to 0. Why? Because I can choose x equal to 0, in this case I will choose y is equal to 0, and that means the inequality now will take the form ax square is greater than 0. Since x is being squared, it's always positive, therefore it also means that a has to be positive. And here also it means, here of course we will take x equal to 0, and the inequality takes the form cy square is equal to 0. Once again, y is being squared here, therefore y is a positive quantity, therefore c has to be a positive quantity. So these are the two obvious restrictions on the coefficients that I have. Correct? Now, can I do more? As it turns out, I can do more. I can recast this equation in terms of perfect squares. How? Well, that's a little bit of an algebra that you have to do. So I can write down this as b over a y whole square plus c minus b square over a y square. If you expand the left hand side, and if you just expand this expression, you will see that this is going to be x square twice b over a xy plus b square over a square y square plus c minus b square over a y square c y square. And if you just do the simple algebra, then you will see that this expression on the right hand side is exactly the expression that we have written down over here. So therefore, this inequality I can recast in the form that a of x plus b over a y whole square plus c minus b square over a y square must be greater than equal to 0. Once again, this would mean that c minus b square over a must be greater than equal to 0, which means that b square must be less than a times c. Note that together with the previous constraint, this one are superfluous, because I already know that a is positive, c is positive. For example, if b square is less than ac and a is greater than equal to 0, then c is also greater than equal to 0. Anyway, so we'll consider all the three conditions together. So we have a positive, c positive and b square positive, right? Once I have this now, let us identify what a, b and c is corresponding to this inequality that we have written down for the minimization of the energy. So it means that a is identical to del T del S volume constant, b is identical to minus del P del V entropy constant, and c is identical to del T del V entropy constant. So a is greater than equal to 0 implies that del T del S at volume constant is greater than 0, which in turn implies that del S del T times T volume constant must be greater than equal to 0. And therefore, you immediately conclude that the specific heat at constant volume must be positive, which essentially means that if temperature is raised, energy must increase. Or in other words, if you give heat to the system, its temperature must increase, because TdS, remember, is equal to d cut q over T. So if TdS is positive, delta T must be also positive, because this derivative TdS del S del T volume constant is positive. So if you if you have trouble recalling things, then you can immediately see that your dt must be del S del T volume constant right. Now b greater than 0 implies that minus del P del V is great, entropy constant is greater than 0. So this essentially means that del V del P 1 by V minus is also a positive quantity, and this effectively means that kappa T must be kappa S, because here entropy as being held over constant over here must be positive quantity. So if pressure is applied, then volume must decrease. Come down to the third equation, the third condition, where we had B square is less than equal to AC. Now B square, in our particular case, B is del T del V, entropy constant. Therefore this whole square is less than equal to minus del T del S, volume constant, and del P del V, entropy constant, right? So now what I can do over here is I will write down this as del T del V, entropy constant square, plus del T del S, volume constant, del P del V, entropy constant, must be less than equal to 0. So now there is a very clever manipulation. If you recall, du was TdS minus PdV, and therefore del T del V, entropy constant, is minus del P del S, volume constant. So I'm going to keep one del T del V entropy constant, and you will see in a moment why I want to keep it, and I'm going to replace the other one, since it's a square, del P del S volume constant minus plus del T del S volume constant del P del V entropy constant must be less than equal to 0. Now can you see that this is T comma P del of S comma V. Why? Because if you just remember the Jacobian, del of F G comma X comma Y is equivalent to del F del Y del X del Y, which was del X F del Y G minus del Y F del X G, where del X is identical to del X and del Y is identical to del Y. Of course, when I write down del X, it means the Y is being held constant. So if I look at this, this is identical to del T del S volume constant, del T del V entropy constant, del P del S volume constant, del P del V entropy constant, which is equal to del T del S volume constant times del P del V entropy constant minus, I'll write down in the next line, minus del T del V entropy constant del P del S volume constant. And this expression that you have seen over here in the right hand side is exactly the expression in the left hand side of the inequality. So we basically very cleverly manipulated this expression into the form of a Jacobian. Therefore now our inequality is del T comma P del S comma V must be less than equal to 0. What can we do now? Again, now I know. So I know how to manipulate Jacobians. So I'm going to write down this as T comma P divided by del of T comma V, del of T comma V del of S comma V must be less than equal to 0. This, from the definition of Jacobian, this implies this first part of it is del P del V temperature constant, and the second part of it is del T del S volume constant must be less than equal to 0. But this derivative del T del S is nothing but specific heat CV. Now CV is positive. Since CV is positive, it follows that del P del V temperature constant is less than equal to 0, which means of course del V del P temperature constant is less than equal to 0. The isothermal compressibility, just as we had defined the adiabatic compressibility or isentropic compressibility, is defined as minus 1 by V del P temperature constant. And since del V del P temperature constant is less than 0, this would mean that the isothermal compressibility is also a positive quantity, which means if pressure is applied, volume must decrease. So therefore, the whole point of this discussion that we have been having for so long is that the stability criteria essentially puts a severe restriction on the response function. The specific hits Cp minus Cv, which is Tv alpha p square over kappa t. Alpha p is positive, volume is positive, temperature is positive, kappa t is positive, and further Cv is also positive. This means that Cp minus Cv is greater than equal to 0, and therefore it follows that Cp is greater than Cv. So the whole the stability criteria that we have minimized the energy, you will get the same identical results if you had used the entropy maximization principle. This means Cv greater than 0, kappa S greater than 0, kappa T greater than equal to 0. So this is the restrictions on my response function. Now thermodynamics puts these restrictions from a different perspective, namely that my equilibrium is a stable equilibrium. If the equilibrium is an unstable equilibrium, then I violate the minimization of the energy principle, the inequality corresponding to that, and therefore all these inequalities, all these restrictions of the positivity of the response function does not hold. Statistical mechanics, when we do it, we will also see that in statistical mechanics essentially you also have the same positivity of the response function. They emerge from a different idea. In StatMech, it's the fluctuations which are more important, and you will see that the distribution of these fluctuations of any physical quantity are very important, and you will see that the distribution of these fluctuations of these physical quantities, the width of these distributions are determined by the response function. We shall deal with it when we come to that. Right now, what we want to write down is Cv is T del S del T volume constant, and therefore this, if I recall, is del 2F del T2 volume constant. Cp, you recall, is T del S del T pressure constant, which is minus T del 2G del T2 pressure constant, and kappa T, the isothermal compressibility, is V del 2F del V2 inverse temperature constant. If you want to write down in terms of the Gibbs free energy, it's minus 1 by V del 2G del P2 temperature constant, right? So Cv is greater than equal to 0 and kappa T is greater than equal to 0, right? And this essentially means that if I look at this expression over here, this would mean that del 2F del T2 must be less than equal to 0. The kappa T is positive would mean that del 2F del V2 temperature constant must be positive. correct? I also have Cp greater than 0 and kappa T greater than 0, which would mean that del 2G del T2P is less than equal to 0 and del 2G del P2 temperature constant must be less than equal to 0. Therefore, the stability criteria of the energy means that the Helmholtz free energy F, which is a function of Tv and n, I am suppressing the n because I have considered it to be a fixed quantity, is essentially a concave function of t because of this, and a convex function of volume. So F is a concave function of t and a convex function of volume. In contrast, the Gibbs free energy G, which is a function of T and P, is a concave function of T and P. So we'll conclude this discussion on stability criteria. I invite you to look at H and omega and to figure out how these functions, thermodynamic potentials, are going to behave. I leave it to you as an exercise. I will also leave you as an exercise that if you start with entropy, where we had started with U as S comma V, if you start with S as a function of U and V, you should do the calculation and see that you will come to the same result.